Hi everyone. How's it going? In previous videos, we've been looking at machine learning algorithms. So the actual algorithm that learns whatever from the data to do classification. Now we're going to turn our attention slightly to look at one thing, which is when we get real data, sometimes it's not in the form that we can readily use these algorithms for. So that's this one-hot encoding we'll be covering. And on the other end, we set these hyperparameters, these certain values. How do we know whether one setting is better than another? And for that, we're going to be looking at cross-validation. So we're going to kind of nest this idea of machine learning into, how to prepare the data, or one aspect of preparing data. And also on the other end is, how do we do an evaluation of whether these hyperparameter settings are good ones or not? So the last thing we looked at was this van example I made up. And the reason I chose this or created it is that it had numeric data. So everything's a number, wheelbase sleeps, whether it's, one person or two people. And when we've been looking at entropy and doing things by hand, we've been looking at this data set, again, a made up example, and it's whether someone should mountain bike or not, based on whether it's sunny or overcast or rain. And the thing here to note is that it's not numeric data, it's categorical data, right? We don't have numbers here. The values are categories. It can be sunny, overcast, or rain. It can be hot, mild, or cool, whatever. We had zero problems with this when we were working with entropy, but for a lot of machine learning algorithms, you can't use categorical data. It has to be converted into a numeric or Boolean data. So that's what we're going to look at. And we're going to use a slightly different example of this. And again, this is categorical data, but we're looking at this one. So suppose we're trying to decide, the goal is to label whether the person liked this particular track or didn't like it. And one of the features is genre. So you can see we have rock, jazz, hip hop, blues, and so on. Again, this is categorical data, right? There's a limited number of categories, but they're not numeric. So one thing we could do to convert them is just give a number to each. So rock can be 1, jazz 2, hip hop 3, and so on. But unfortunately, what this does, it implies some sort of ordering, right? It implies that, for example, jazz is close to rock, right? They're only 1 different. Then rock is to blues, which is 3 different. And rock to country, which is 6 different. So it implies this ordering that isn't present. And we see that in this iteration, country is pretty close to classical music. And we think, well, maybe we can get clever and fix this. And so we'll say, well, rock's 1, and maybe blues should be 2, or maybe blues should be 1 and rock 2, and then country 3. But no matter how clever we get, we can't solve this problem because these categories aren't numbers, right? There's no ordering to these categories. So this approach doesn't work. The approach that does work is to kind of flip things a bit. So here we have these values of a category, genre, and those values are rock, jazz, hip hop, blues. We're going to use those values and make them their own columns. We're going to have a rock column, a jazz column, a hip hop column, and so on. That's going to look like this. So we've converted this into columns, and if the Beatles' Hard Day's Night is a rock song, we're going to put a 1 there, and if it's not jazz, we'll put a 0, not hip hop, not blues, and pop. So this is the solution, and it's called one-hot encoding, right? So if the value is 1, it has that value. 0, it doesn't have that value. And one benefit is that things can have multiple values. So this Thelonious Monk Blue Monk song can be both a jazz tune and a blues tune. So that's one-hot encoding. Let's see a demo of how to implement that. All right, so here we are in a Python notebook, and we're going to look at that mountain bike example and examine one-hot encoding. So the first thing I'm going to do is import that data set. And we see that we have these values, sunny, overcast, rain. And I'm going to just do the standard stuff of divide things into features and labels. There's my features, or the names of the features. Okay, and now we can create those 2 data frames, or And let's just look at those bike features. Okay, so no surprise, looks good. Now let's attempt to train a classifier. And fit it to the data. And here we see that problem of trying to use categorical data with these algorithms. So it says could not convert string to float, sunny. So this is an indication that we need to one-hot encode these columns. Now I'm going to show you a couple ways. One way is, it's probably not the best way, but it really is pretty good at illustrating what the issue is and how things work. And the other way is more useful for large data sets especially, but it's not that illustrative of how the process works. So one is good at helping you understand how things work, and the other is probably more beneficial in practice. So I'm going to go with the one that illustrates the solution the best. And for that, we're going to create a new data frame of one-hot encoded values for one of the columns. Let's take Outlook. Then I'm going to drop that Outlook column because we don't need it anymore. And then I'm going to join that new one-hot encoded data frame to the original. And we'll see how that works in a second. So let's do that. I'm not sure I imported pandas, so let me just do that. Okay. And sadly, I'm getting that. And I'll just make a copy because I don't want to wreck the original. I might need that later. And let's one-hot encode that column of Outlook. There's this function getDummies that will do that. And let's just take a look at our result here. And we see that now those values overcast, rain, and sunny, which were the values of that Outlook column, now have turned into their own column. So we successfully one-hot encoded one of the original columns of the data set. Now we're going to drop that Outlook column. And we're dropping a column, not a row. Just let's take a look at that. Okay, and you see we no longer have that Outlook column. Now I'm going to append that those one-hot encoded columns. And let's just take a look at that. Bike features 1. Okay, so now we see that we have those 3 additional columns: overcast, rain, and sunny. Now we could go ahead and do the same for wind, humidity, and temperature, right? But let's automate this a bit. So I created this function, one-hot, that will do that, go through all the categories and one-hot encode each category or each column, and then drop the original column and append it. One thing I did do here was do this prefix equals category part of getDummies. And what that does, we'll see shortly, but it appends a prefix to each value. So let's say we had, I don't know, true values, true, false, and maybe in a couple columns. Well, it'd be hard. We wouldn't want columns that were just called a bunch of trues. We'd want to know which column originally it was. So that's what this prefix does. So let's use that function to one-hot encode the data. So one-hot. I think I called it features. Let's make sure that works. Oop, it helps to run that function, doesn't it? So the prefix puts the original name of the column in front of the value. So overcast, or Outlook overcast, Outlook rain, Outlook sunny. So that looks all good, and you can see what it does. That's what I liked about this method, and explaining it to you is that you can easily see how it works, that it puts a 1 if that was overcast, and then zeros in other places. So number 3, here's an instance where it was overcast, the temperature was hot, and so on. And the original looked like that, so you can see what the, what we did to it. So we kind of flipped things. That's the way I describe it. We are flipping these values to turn them into their separate columns. But for larger data sets, it's not great to do this method because, if we had 100 columns and each column had 5 different values, we'd end up with 500 columns in the end. So that's really not, it's going to be some huge expansion of our data set. So there's a better way. And that better way is to use sklearn's one-hot encoder. So let's see how that would work. And what sklearn's one-hot encoder does is create what's called a compressed sparse row format. Compressed sparse row format. You'll learn this. And it's also known as the Yale format. And I think there's a couple other terms that people use. You'll see how it looks in a second. And the first thing we need to do is import it. I'll create an instance of that one-hot encoder. Okay, and now I'm going to, in one swoop, figure out what the encoding should be and actually encode that new data frame. I'll call it byte sparse. So for that, I'm going to use the function fit. Whoop. And also transform the data. And the original thing was byte features. So there, hopefully it did it. And let's take a look at it in what that sparse row format looks like. For that, I'm going to have to import some other stuff. That looks good. So what this format is, this Yale format or compressed sparse row format, it creates 3 arrays. So it always creates 3 arrays. And here's how we read it. Let me see if I can kind of scroll this enough. So the first, or let's look at the second array, the 0, 0, 0, 0. That is what's true with this category Outlook overcast, right? So we're looking at this 0th column. That's this array here. This first array says which row. So row 2, column 0, row 2. Column 0, row 2 is here, and that's where 1 is. And this is the value in the third array that goes there. It's 1. They're all 1s. It's either 1 or 0. So this third array is always 1s. The next one is 0, 6. So 0th column, 6th row is 1. So as you can see, it's only encoding where the ones are, or only encoding where the non-zero values are. So that's what this sparse format does. So it's hard to see, and the reason I chose the other one, it's nice to see that those ones and zeros, here you don't. It's a little bit more work involved in figuring out what this looks like, but it's much better when we're using large arrays or large data sets. So let's go back to our classifier and see if we can fit it. I've already created that classifier up above, that one that gave us that nice error. And I'll use that sparse data set. So even there, though it looks kind of funky, that those 3 arrays, it works fine for sklearn's fit. And then we had bike labels. And it had no problem. It worked perfectly. So now let's take a look at it. And there you see our decision tree, right? So it knows enough. So the first column, whether it was overcast, if it's less than 0.5, meaning it wasn't overcast, then we go this way down the tree. So hopefully we can make some sense of this, even though it's using that sparse format. So that's cool. So that's one hot encoding. Now let's go back and talk about the next thing we're going to talk about, which is hyperparameters and how we do cross-validation. All right, so hyperparameters and cross-validation. So we create this decision tree classifier. We say, hey, give us a decision tree classifier. But our work isn't done there. There's still things we can adjust before we fit or before we train that classifier, right? So we can say whether we're using entropy. We've always been using entropy, but we could use something else, some other measure like Gini. We can limit the depth of a tree. So instead of letting it go to its completion, we can say, hey, limit the depth of this tree to 6 or whatever. And we can limit when we split a node. Only split a node if there's a minimum number of 5 elements or something. So we have a number of hyperparameters. These are hyperparameters that we can adjust. And that's true of any classifier. So this is the decision tree one. But every classifier we see, there's going to be these little things I have inside there that I'm representing these hyperparameters. So we take that kind of blank slate classifier and some labeled data, and then we train a classifier, right? So finally it learns something. So a decision tree classifier is going to learn that decision tree. And then we can take that test data in and figure out, well, what's the accuracy of this classifier? It's 80% accurate. So we've made some adjustments, say, we've created a classifier, say, limit the depth to 8. We trained it, and then we get some sort of accuracy. And let's say we do it again. We make some other adjustment, limit the depth to 10, and rerun this whole system and see what our accuracy is. Now it's 87%. And we keep doing this. We might adjust the hyperparameters and keep going until we get the best accuracy we possibly can. It makes sense. So again, once we select a classifier, we still have some work to do in adjusting these hyperparameters. So again, the parameters are things the algorithm learns, and these will become a lot clearer when we're talking about deep learning. It's really easier to understand what these parameters are. Decision trees would be the rules. So parameters are the rules that the algorithm discovers. Hyperparameters are what we can adjust, what we, the developers, are adjusting before the algorithm does any learning. So how do we know what's the best one? How do we know that, whether max depth 4 is good or maybe max depth 7 is better? Or what should be the minimum samples in a leaf? Or whatever these hyperparameters are, how do we know one's better than another? So we might think of it this way. So we're going to take some labeled data and divide it into training and test. We've done this before. And now we're going to take that training data and along with the classifier and train the classifier. We run that trained classifier on the test data and see how accurate it is, right? And then we're going to loop back in this system. So we get 80% accuracy. We'll try again. So we'll take that classifier, adjust some hyperparameters, change the max depth, and try again and get some other accuracy. But the problem with this approach is that information is leaking into the classifier, information about that test set, right? We're tuning the classifier to do well on that test data, right? Because there's that feedback loop. We're going to keep improving, altering the classifier until it does super well on the test data, but that information about the test data is leaking in to the classifier. So this is really not a good method. We're not going to get a very accurate accuracy measurement, right? It's tuned to that test data. And so if we report at the very end, we get 93% accuracy, maybe not. Maybe if it was brand new data, we wouldn't get it because we really tune that to the test data. So here's what we should do instead. We're going to take label data, and then we're going to have three kind of bins of data. We're going to have training data, the validation data, which is the data we're going to use to adjust these hyperparameters. And at the very end, when we think we have the best possible classifier with the best possible settings for all these hyperparameters, we'll evaluate it exactly once on that test data, and that's what we'll report. This is how accurate our classifier is, because it's run on data that we haven't done any adjustments to the classifier. We're just running it on the test data and we can report it. So no information that's in that test data is leaking back into that classifier. So it's going to work like this, that we have the classifier and some labeled data and we train it, and then we evaluate it with this validation data, and then we get something like 80% accuracy. And so then we adjust the classifier again, the hyperparameters, and run it again and see what accuracy we get. And at the very end, once we have the very best classifier we can, we run it exactly once on the test data, and that's the accuracy we can report. Hey, this is how accurate we are. It's data the algorithm's never seen before. We haven't even seen it. This is the best accuracy we can get. So now the question is, how do we divide this up? How do we decide how much goes into training, validation, and test? And we could say, well, let's see. So training, maybe 70% of the data, 10% for validation, and 20% for test. It's up to us. But the best method is to do something called cross-validation. And let's see how that works. So we're going to start with dividing the data the way we did before. We're going to have labeled data divided into training and test. We reserve that test for the very end of our experiment. And now what we're going to do with this training data is divide it into 10 buckets. 10 is tenfold cross-validation. We could do sixfold cross-validation with 6 buckets. I don't know why no one would probably do it, but you could do 100-fold cross-validation. I'm picking 10 here because it's kind of the most common approach. So we divide the training data into 10 buckets. We divide it kind of equally. So if there's 90% of the people have this, don't have this disease and 10% do, we make sure that those buckets represent that split, that 90% of the people in bucket 1 don't have whatever we're testing and 10% do. So we're kind of stratifying the sample. So what we do then is we train the data on 9 of the buckets. So in the first case, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, those first 9 buckets. And then we're going to evaluate or validate the thing on bucket 10. So we're reserving 1 out every time, right? So we train on 9, evaluate with 1. Then we're going to do it again. This time we're going to leave number 1 out and train on 2 through 10. So we'll evaluate on 1 and keep doing that. So we're going to leave 2 out, train, and then evaluate or do that validation on 2, 3, 4, keep going. So each time leaving 1 bucket out and evaluating the algorithm on that. So after 10 iterations, we've trained on all the data, right? So we've trained on 9 buckets, but we keep leaving 1 out. But eventually we've trained on every single amount of data. And we also validated on all the training data, although we never validated on the data we trained on. So in an instance of running through the algorithm, when we trained on 9 of the buckets, we evaluate or we validate the algorithm on just the 1 left out. So it's never the case that we're validating a classifier on the data that we trained on. All right, so let's see how this works in practice. And cross-validation, I'm going to use a data set that has to do with these phased array antennas. This isn't the picture of the exact phased array antenna that we're looking at. I couldn't find one, but they look sort of like this apparently. And it's originally from this article, Classification of Radar Returns from the Ionosphere Using Neural Networks. So we're using the data from this article. And they have 16 antennas, and they get 2 values from each. And the label they want to predict is whether that measurement is a good one, meaning we need to do further analysis on this reading, or if it's kind of a dodgy one that we're just going to ignore later on. So let's get that information in. And you can see that here's the data. It's all just numeric except for that last column, which I'll show you in a second. Okay, and this is just some general information about it. The columns has 351 rows and 35 columns. That last column, there's 34 columns of features, 1 column that has the label. And let's look at that label column. So it just has G for good and B for bad. So we're trying to learn that based on these real values of what we're getting back from this phased antenna array of 16 antennas. So here I'm just kind of doing the general stock stuff that we've already done, so I didn't want to just bore you by typing it all in. So here we split into a training set and a test set, and then I divide it into features and labels and for both. So I have radar train features and radar train labels, and the same for tests. So let me just execute that. And there we get the labels are these goods and bads. Okay, now let's create a classifier, and I'll just call it my standard CLF. All right, so here are the cross-validation steps. The first thing we need to do is kind of import that cross-validation score, and this is how you do it. And it helps to spell learn right. That looks better. All right, and now we're going to run that cross-validation, and here's how you do it. So it's going to give us 10 values back because I'm going to create a cross-validation instance that has 10 of these buckets. And we're using that classifier we created. The test set is radar train features. Whoop. Whoop. And now I'm going to say how many buckets to use. Cross-validation of 10. And great. Let's see what I did wrong here. Radar train test. Oh, geez. Radar train label. Sorry, my error. This is doing, it's performing that tenfold cross-validation on all that entire data set. So it's running through this 10 times. So it says here, so CF10 specifies we perform 10 of them. So for accuracy, let's take a look. It didn't take very long to do that, did it? So let's just look at the scores in general. That looks good. So there we go. So we get the 10 accuracies of running through it. Remember, leaving one bucket out. And then we get that average of, once we run it through 10 times, what that average is. So scores is the accuracy for each of the 10 runs. So now we've done it for one set of hyperparameters, and now we want to investigate, well, maybe if we set the max depth to 5, that thing would be a little better. So let's give that a shot. I'll stick with the CLF as my thing. Let's say max depth equals 5. Okay, and here's with that one, I'm just doing the same thing we did before. And it's not as good, right? So we didn't do as good as before. And we could try it again. Maybe max depth of 7 would be good. And we get 8. So that's not as good as the first one. So we can keep trying. All right. So once we're finished with figuring out, well, what is that best settings for these hyperparameters, we can train a new classifier on the entire training set. So we're not leaving one bucket out. In this case, we're training it on the entire training set because we found what we think are the best hyperparameters. So let's do that. I'll just call it final CLFF equals tree. And let's say it was the one where we didn't specify the size, and now we need to fit it, I guess. Might be a good idea. Okay, so we have that best classifier, we think, and we can test it on the test data. Remember, we haven't done anything yet with this test data. This is the first time we're using it. We've tuned up the algorithm without ever looking at that test data. That's the kind of the important idea. So let's make predictions on that test set. Radar test features. And I'm not sure I imported the accuracy score, so let me go ahead and do that. And then let's get it. And the correct labels are and the ones our algorithm predicted were in predictions. And so there, the best one is 88% accurate. So that's kind of how we'd go about doing it, right? So we have the test data we never see. We do cross-validation, meaning we have a number of buckets, often 10, and we train 10 times. We go through those buckets, always leaving one out when we train the data and using that one that we left out for validation. But you can see that if we're testing all sorts of options for these hyperparameters, like here I say if we want to find the max depth and we want to check the values from 3 to 12 and the min sample split from 2 to 5, that makes 10 values for max depth, 4 for min sample. So if we did all those combinations, we'd have to create 40 different classifiers. And man, that would really be a hassle to do all that by hand. But fortunately, there's obviously there's a better way, since we can have the computer figure that out. So we can run cross-validation against all sorts of combinations of what the hyperparameters are and find the best setting for these hyperparameters. So let's see how we can do that. So we're going to need to import that fancy module that'll do that for us. And it's called GridSearchCV. And now I probably should have done this ahead of time, but we need to specify what we want to test. So I'm going to just call it the Hyperparameter Grid. It's nothing And one parameter is max depth. And I'll just manually 3, 4, 5. Not the best way to do this. And let's also evaluate min. And let's say we want to evaluate those. All right, I think that's good. Let's see if it complains. No, it didn't. All right, so now we're going to start off with just creating a generic decision tree classifier. I've done it a bazillion times, and we're going to do it again. And I'm just going to set the entropy. All right. So we have this decision tree classifier that hasn't been trained. We have the hyperparameters we want to evaluate. Now we can use that GridSearchCV to find the best setting. So I'm going to call it grid. Oop. We give it a classifier. And then we give it also that hyperparameter thing I created, the Hyperparam grid. And we give it how many buckets we're going to use, just like we did before. And if everything goes right, so the classifier, when we created this, we passed it the classifier. We gave it a Python dictionary containing the hyperparameters we want to, it's actually a list of dictionaries that contain the hyperparameters we want to evaluate, and then how many bins we're using, CV10. So we created that. And now for the time-consuming part, which is actually where it's going to go through and run the code. So let's do that. Oop. And now it's running through all those options, right? It's running through for each parameter thing. For each setting of parameters, it's going through those 10 buckets. So it's running through that 40 times. And now we hopefully will have the best classifier. It'll determine the best setting. So we can ask that by saying, what are the grid search best params? And it says the best setting is max depth of 3, minimum sample split 2. Let's hope that's good. Oops, I misspelled classifier here. And we can get the best classifier. To get the best classifier, it's, well, I'll just do it. Let's get the predictions, just to kind of jump ahead and get the predictions of the best classifier. Grid search was the name of our GridSearchCV instance. The best estimator is give me the best classifier you found. So now we have a classifier. I'm going to use that to do predictions and radar test features. So we've never seen the test features. And now let's get the accuracy score. The labels were radar test labels. And the predictions were predictions. And we get a 90% accuracy. So that's really pretty good. So that's what I wanted to show you. So how, when we are adjusting all these hyperparameters, what's the correct method for evaluating that? The correct method isn't to run the test data. It's to have another bucket called validation data. And the best way to do that is to use cross-validation. This all gets tedious by doing it by hand. So we can have the computer do it, that's searching through to find the best hyperparameters. So I hope this was all helpful. See you in the next video. Bye.